New section, the seventh one, real exponentiation part 2. So the section starts like this. Here the author is saying that we have already defined exponentiation, in which we now know the meaning of this x to the power q, where x is a positive real number and q is any rational number. But we have not yet defined x to the power alpha, where alpha is any real number, not necessarily rational. So that's what we are going to do. And in order to be able to do that, we need a lemma which is titled continuity of exponentiation. So let us start with the statement of this lemma. It goes like this. Let x be positive and let alpha be a real number. That is, both x and alpha are real numbers and x is positive. Alpha is any real number. Now we are going to consider a sequence of rational numbers converging to alpha. Let Qn be any sequence of rational numbers converging to alpha. To the real number alpha. Then this sequence whose nth term is x to the power qn is also convergent. Note that we know what these terms are, x to the power qn, because the qn's are rational. Okay, we are not using any power of x where the exponent is a general real number. That's what we are going to define. No? But we know these things, x to the power qn, because each qn is a rational number, and we are claiming that this sequence of real numbers is going to be a convergent sequence. Is also convergent, or is a convergent sequence, same thing. Furthermore, if qn prime is any other sequence of rational numbers converging to alpha, then the sequence x to the power qn prime is also convergent. That's what we have already said, but it is also, besides being convergent, has the same limit as this sequence. The exact words are, then this sequence has the same limit as this, that is, limit of this sequence is equal to the limit of this other sequence. We need to first prove this lemma, this result. So let's now go through the proof. Note that we are just simply saying that these sequences are convergent. We are not saying anything about what the limit is. It is some real number. Okay, we don't know, but a limit will exist, and we need to show that. So in the beginning itself, there are three cases. X is greater than 1, x is equal to 1, and where x is less than 1. And this middle case is somewhat trivial, because here x is not, x is fixed, it is equal to 1, and any power of x where the exponent is rational is also 1. So that's what the author also is saying. The case x equal to 1 is rather easy. And the reason is that because then any such power is equal to 1. For any rational number q. Okay, so that means if our x is 1 and the setup is this, that is, you have a sequence of rational numbers qn that is converging to alpha, then your sequence x to the power qn in this particular case where x is 1 is the constant sequence, all of whose terms are equal to 1, and that of course converges, it converges to 1. Okay, and you can also note that it does not matter what the sequence qn is or what the rational numbers in it are. That does not matter, because whatever these qn's are, this sequence is going to have only one, all the terms are going to be equal to 1, only one value. So Irrespective of your choice of Qn, in this case, this common limit is going to be 1. So in this case, the conclusion of the lemma is trivial. So that's why we are not going to write anything more than this about this case. And the author is going to, in this proof, we are going to see only this case, and this one is left to us, which we will settle when we solve the exercises. Means there is only one exercise, but I will create another one for this one. We shall just do the case x greater than 1 and leave the other case x less than 1, which is very similar to the reader. That means to us. It has been left to us. So there are two parts of this lemma. First, we have to prove that this sequence is convergent, and then uniqueness of limit. So we are going to first prove convergence. Let us first prove that the sequence x to the power qn, where n varies over the set of positive integers, is convergent. How exactly are we going to proceed? We are going to exactly show that this sequence is a Cauchy sequence, because we already have proved that result where we showed that when we are talking about sequences of real numbers, Cauchiness and convergence are equivalent. So it's enough to show that this sequence is Cauchy. Convergence would then automatically be a consequence. So, and the exact result is this: by proposition 6 for 18. It's enough to show that this is a Cauchy sequence. Okay, now for that we need to estimate the distance between any two terms of this sequence. We need to show that the distance can be made as small as we wish in a precise way, which comes from the definition of Cauchiness. Should I write the exact? Okay, let's just write what Tau has written. To do this, we need to estimate the distance between x to the power qn and x to the power qm, where m of course like n is some positive integer. Let us say for the time being that q1 is greater than or equal to qm. Either this or q1 will be less than qn. We will come to that other case later. First we handle this, so that x to the power qn is also greater than or equal to x to the power qm, and this inequality follows from this one, since x is greater than 1. These are available in the rules of exponents that we encountered earlier in one result. We had all the rules of exponents where the exponents are rational numbers. Okay, so we are using that result, although we are not explicitly mentioning that. It's understood what we are doing here. Okay, now what do we have? The distance between x to the power q1 and x to the power qm, because of our choice, and which leads to this inequality. Because of that, there is no need to use the absolute value function. We can just write this, because we know that this is non-negative due to this inequality. Now one can write this thing like this: qn minus qm minus 1. Okay, now what? Now we are going to use the fact that the sequence of rational numbers qn is convergent. Its limit is that real number alpha, and being a convergent sequence, it is bounded. This is a result we have already proved. Every convergent sequence is bounded, and in particular this means that there is an upper bound. Since this is convergent, it has some upper bound m, which is some positive real number. Since x is greater than 1, this implies x to the power qn, or because we need this m, right? X to the power qm is less than or equal to x to the power m for every positive integer small m. Hence, the distance between x to the power qn and x to the power qm, which we have shown, is equal to this qn minus qn minus 1 is now less than or equal to x to the power m times this. Okay, do you see one thing in this final inequality? How are we getting this final inequality? By multiplying both sides of this inequality by this quantity. So, can we do that? We cannot do that if this quantity is a negative real number, but it is not. It is a non-negative real number, and that is coming from here. Due to this inequality, this is a non-negative real number. So in this product, these two must also be non-negative real numbers. In particular, this is not negative. So this final inequality is obtainable. It is true. Okay, so far we have estimated this much. And now we are going to do something with this difference, this exponent. Now, let us denote this difference by r. Okay, so this is rn minus qm. Are we going to use this difference? No, that will come later. Okay, this is not yet, I mean, we have not reached that stage where we are going to use this difference. Now we take a positive real number epsilon, our familiar epsilon, and we want to show that our sequence x to the power qn is eventually epsilon steady. Okay, because then by definition it will be a Cauchy sequence. So we proceed like this. We know from Lemma 653 that the sequence x to the power 1 over k varies over the positive integers, is eventually epsilon times x to the power minus m close to 1. What is this? Recall that in this lemma we proved that this limit exists and is equal to 1. So from this limit, what do we get? If we choose a particular value of epsilon, then after some stage, the distance between x to the power 1 over k and 1 is going to be less than or equal to that epsilon, starting from that stage onwards. That means this is going to be less than or equal to epsilon. Now for epsilon, we are not just simply choosing this epsilon, but we have decided to take this somewhat modified value. For technical reasons, this will be useful later. This will happen after some stage for k greater than or equal to something, some positive integer. And we express this situation by also saying that the distance between x to the power 1 by k and 1 is less than or equal to this. For k greater than or equal to this, in the other language we express this like this: x to the power 1 by k and 1 are this close eventually. That means after this some stage. That's what we have written here. We know from Lemma 653 that the sequence is eventually this close to 1. The sequence itself is eventually this close because all the terms starting from that stage are this close to 1. So that means in this final line, this is what we are saying in words. Thus, then again we are writing also that as an inequality. Thus, there exists a positive integer k such that the distance between the corresponding term in the sequence and 1 is less than or equal to this modified epsilon times x to the power minus m. Although we are not mentioning every last detail, note that we should be able to choose this new modified epsilon. In other words, it should be positive. It is positive. From our properties of exponents of a positive, properties of powers of a positive real number, where the exponent is a rational number, we know that such powers are always positive. So x to the power minus m, in spite of having a minus m negative exponent, x to the power minus m is a positive real number. So this product is positive, so it can be chosen in place of epsilon. So there exists a positive integer k such that x to the power 1 over k minus 1, which is equal to the absolute value of x to the power 1 over k minus 1, this is less than or equal to this. And because x is greater than 1, any kth root of x is also greater than 1, which I think either we came across this fact in one of the results, or we proved this thing in one of the exercise solutions. You go back to the exercise solutions, there you will see that somewhere we proved that if x is greater than 1, then any kth root where k is a positive real number, positive integer, is also greater than 1. So that's why we can remove the absolute value here. So we are now here. Okay, so convergence of the sequence Qn leads to it being bounded. We have used that fact and we have got some things. Now convergence, again convergence of Q1 also means it is a Cauchy sequence. We are next going to use that fact. Since is convergent, it is Cauchy, and hence so there exists a stage starting from which Qn and Qm, these two terms of the sequence, can be made as close as we want. There exists a positive integer n such that Qn and Qm are what close? How close are they? 1 over k close. As close as we want. Right now we want them to be 1 over k close. That means we want their distance between them to be less than or equal to 1 over k. For all indices n and m greater than or equal to that stage n. Hence, so with this new information, what happens to our inequality? The distance between x to the power qn and x to the power qm, which now is less than or equal to x to the power m times x to the power qn minus qm minus 1, is less than or equal to x to the power m times x to the power 1 over k minus 1. Let us carefully see what we did in this last inequality. We are saying that Q1 and Qm are 1 over k close. So that means this inequality is true. And recall that because of our choice, Qn is greater than or equal to Qm. So this, we don't need to use the absolute value. This implies x to the power qn minus qm is less than or equal to x to the power 1 over k, because x is greater than 1. And then subtract 1 from both sides. So this becomes less than or equal to, this minus 1 becomes less than or equal to this. Multiply on both sides by x to the power m. So that gives you this final inequality. And x to the power m is positive, so we can multiply without altering the direction of the inequality. So that's what we have done here. So far the steps are justified. Okay. But we have an inequality for this term also. No? This is less than or equal to epsilon times. So now we write this is less than or equal to x to the power m times epsilon times x to the power minus m. So now you know why we decided to take x to the power minus m, because now these two things will get cancelled and we will be left with epsilon. And this entire thing is happening for all n and m greater than or equal to that positive integer capital N. So that means we have been able to show that x to the power qn and x to the power qm are epsilon close eventually. Hence, they are epsilon close, so the sequence itself as an entity is epsilon steady eventually. Hence, the sequence x to the power qn, where n starts from capital N, is epsilon steady which implies the original sequence where n starts from 1 is eventually epsilon steady. But epsilon also is arbitrary. So this eventual epsilon steadiness is true for any positive epsilon, since this is arbitrary. We conclude that our sequence is a Cauchy sequence. So being Cauchy, it is convergent. So we have shown that it is actually convergent. Note one thing, that it does not matter what the sequence Qn is, what type of terms it has. Its terms may be large also. For example, Qn, you can consider this sequence. This is a convergent sequence. From our laws of limit laws, we know that this sequence converges to this number. All the terms are quite big. The limit is also quite big. So you can understand that if you take x itself to be quite big, everything will be gigantic. If you take x equal to 100, you can imagine how large the terms of this sequence will be. 100 to the power this. But in spite of that hugeness, unimaginable vastness, still this sequence is convergent. It converges to something. Okay, so we are done with one half of the proof. Now we come to the question of uniqueness of this limit. We now prove the second claim. It will suffice to show that this limit is 1. X to the power qn minus qn prime. This limit is 1. For then one can use the limit laws to derive the desired conclusion. Since the claim would then follow from the limit laws. Because x to the power qn equals x to the power qn minus qn prime times x to the power qn prime. So if you manage to prove that this sequence converges to 1, then on both sides you can take limit, and the limit law, one of the limit laws tells us that the limit of the right hand side is the product of the limits of the individual sequences. This sequence has limit 1 and this sequence has some limit, and that some limit will be equal to the limit of this one, and that's what we want. Note one thing, don't forget that we have already shown that such sequences are convergent. That's what the first part is. Okay, now write, and now we have come to that stage where we can consider a difference, but it is not the difference I was thinking back then, qn minus qm, no, it is this one, Rn to be the sequence whose nth term is qn minus qn prime. By the limit laws, we know that, or rather from the limit laws, we know that the sequence Rn converges to 0. Let me use some ink. We have to show that for any positive epsilon, the sequence x to the power Rn is eventually epsilon close. Sequence is eventually epsilon close, we are saying. Is that a Yeah, sequence is eventually epsilon close to 1 means after that stage all the terms are going to be epsilon close to 1. Yeah. Okay. Sometimes these languages become a little confusing because they are not standard languages found elsewhere in mathematical literature. They have been devised by Terence Tao himself for the sake of simplifying the definitions of Cauchy sequences, convergence, and so on. Eventually epsilon close to 1. Okay. Now how are we going to show that? By lemma, okay, again we are using lemma 653. By lemma 653, the sequence x to the power 1 over k is eventually epsilon close to 1. Because it converges to 1. Also, since we have this limit as well, okay, lemma 653 tells us that this sequence converges to 1. So by the limit clause, the sequence obtained by taking the reciprocals of the terms also converges to 1, and we can take the reciprocals because all these powers are positive, none of them is 0, and thus we have this limit. Now this again implies, and this is coming from this lemma of course, by lemma 653, the sequence x to the power minus 1 over k is also eventually epsilon close to 1. Hence, there exists a positive integer k such that we already used one capital K there in proving part 1, but that thing is gone. Okay, that is finished. So now we are again ready to use whatever letter we want, such that both x to the power 1 over capital K and x to the power minus 1 over capital K are epsilon close to 1. There is something in between, I mean an intermediate stage is there before one can write this final conclusion. See, what we are saying here is that this sequence is eventually epsilon close to 1. What is the meaning of that? The meaning is this: there exists a positive integer m1 such that this inequality, this is small k, okay, is less than or equal to epsilon for all k greater than or equal to m1, because eventually epsilon close. This is also eventually epsilon close to 1. So there exists a positive integer m2 such that we will have to the power minus 1 over k. This is less than or equal to epsilon, where k is greater than or equal to m2. So where is this capital K coming from? Capital K is greater than both m1 and m2. I mean, whatever m1 and m2 are, you can of course choose an integer k greater than both of them, because positive integers have no upper bound. So for such a k, both these inequalities are going to be simultaneously true. That's why we can write that there is a positive integer k such that both this and this are epsilon close to 1 at once. Oh, this is not a part of the proof, so let's just wrap this up. R epsilon close to 1. Now, since Rn, let us now again think of the sequence Rn, which recall is the, Rn is Qn minus Qn prime. Oh, I forgot to say why Rn converges to 0. No? We just said that by the limit loss it follows. That is just simply this. Qn prime. At this step you apply one of the limit laws, minus limit of Qn prime, and both these limits according to our hypothesis are alpha. That's why you get 0. Okay, now since this is convergent to 0, it is 1 over k close to 0, and that too eventually. You know what that means? It means that we have this for n greater than or equal to some integer. So it is 1 over k close to 0 eventually, so that, and what do we get from this? This inequality, only this one is equivalent to this, which is equivalent to these two inequalities, and all these things are happening after some stage, so eventually, so that eventually minus 1 over k is less than or equal to Rn, which is less than or equal to 1 over k. And from these inequalities we can now get the corresponding other inequalities involving x. Thus x to the power minus 1 over k is less than or equal to remember we have been able to translate the inequalities involving q and rn and such rational numbers to inequalities involving powers of x because x is greater than 1 and the inequalities have not changed direction. It is because of x being greater than 1. If x is less than 1, the inequalities, all of them will get reversed. This is one over k eventually. Now what is the implication of these inequalities? In particular, the sequence this is eventually epsilon close to 1. How exactly? For that you see proposition 437 part F. Actually what that what this proposition says, what part F says is this: say x and y are two rational numbers which are epsilon close to something, okay, says to z, and you have an intermediate number w which lies between x and y, then w will also be epsilon close to z. So that's what we have used here, and in place of x we have x to the power minus 1 over k, in place of w we have x to the power rn, and in place of y we have x to the power 1 over k. Now I said rational, but this proposition was later extended to real numbers also. Okay, so that thing actually we are using. So we are not saying by this proposition, but by the version of this proposition involving real numbers. And let me just see, x to the power 1 over k and x to the power minus 1 over k, both these things are epsilon close to 1. Okay, and these inequalities are eventually true. That means they are true for all n starting from some stage. So starting from that stage, all these x to the power rn's are going to also be epsilon close to 1. That means this sequence is going to be eventually epsilon close to 1, and that's what we wanted to show, because now that means that this sequence converges to 1, and this sequence converges to 1. 1 means those two limits are the same thing, they are identical. So here the proof ends. Now using this result we make this following definition. We may now make So this is definition 672 and it has this name, exponentiation to a real exponent. And it goes like this: let x be greater than 0 and let alpha be a real number. The author writes let x greater than 0 be real, but it's understood, okay. And let alpha be a real number. That means x and alpha are real numbers where x is positive. We define the quantity x to the power alpha by the formula this is the limit of x to the power qn as n approaches infinity, where qn is any sequence of rational numbers converging to the real number alpha. Okay, so the meaning of x to the power alpha is this. X to the power alpha means this limit to which the sequence x to the power qn converges. It is also some real number. Let us check that this definition is well defined. That is, using this definition, are we now going to be able to define x to the power alpha unambiguously and in a manner that makes sense for any positive x and any real number alpha? That's what we have to check. Since alpha is real, there is at least one sequence qn, let me write it there, of rational numbers converging to alpha. Why? Because that's how we have defined real numbers, right? For us, real numbers by definition, they are formal limits of Cauchy sequences of rational numbers. But then using one result which we later came across, formal limits are genuine limits also. So that's why if you have a real number, that means in the background of that real number there is a Cauchy sequence of rational numbers whose limit is that real number. And we can write by the definition of real numbers and that result, which is proposition 6.1.15, which says that the formal limits of Cauchy sequences of, or in other words, the formal limits are genuine limits. Precisely, if you have a Cauchy sequence of rational numbers, then you have two kinds of quantities attached to it. One is the formal limit of the sequence and the other is the actual limit of the sequence following the definition of limits of sequences of real numbers. This result shows that those two things are actually the same thing. Okay. So, by the thing we have seen now, the result by lemma 671, the sequence, or we can directly write like this: the limit exists. So we have a value, a real number here, and the other thing is that this limit is independent of the choice of the sequence given. Also, by lemma 671, the second part, you have decided to start with the sequence Qn which converges to alpha. Someone else may decide to start with some other sequence of rationals, say Qn prime. The result we have proved just now, it says that those choices are not going to affect the limit of x to the power Qn, this limit. The limit you are going to get is the same, both of you. If Qn is any other sequence of rational numbers converging to alpha, then this limit is equal to this limit. So our definition of the quantity x to the power alpha gives us a unique real number for a given positive x and any real number alpha. So that's why the definition is well defined. Thus, definition 672 is well defined. This definition gives us an answer to that question which occurred in some situation. What is the meaning of this number? But how do you define this number? Now we know what it is. Root 2 is a real number, so you can think of root 2 in place of alpha, there is some sequence of rational numbers converging to root 2. Okay, so what you do, you consider this sequence 2 to the power qn. This sequence by this result converges to something, and that something is written like this. That's what 2 to the power root 2 is. So we have now extended the powers to those powers where real exponents are allowed, but there may be a problem. If alpha is not just real, but in fact, in particular, rational also, that is, if alpha is equal to q, for some rational number q, then there may be a potential problem with the new definition and the old definition of x to the power alpha. They may not give you the same, I mean, it's not a priori known that they are going to give you the same meaning of x to the power alpha if alpha is rational. Luckily, that of course does not happen. We will get the same thing. Then okay, let me just simply write what Tao has written instead of coming up with some language of my own. Then this definition could in principle be inconsistent with our earlier definition. Be inconsistent with our earlier definition, which is definition 567. Why? Because you see, there are two interpretations of x to the power alpha now. One of them, of course, is like this. You find a sequence of rational numbers that converges to your alpha. Then you consider the sequence x to the power qn. It converges to something, some real number, and that real number is x to the power alpha. This is using the new definition. The old definition, however, is something else entirely, because now our alpha is a rational number. So being a rational number, you can write alpha as a quotient of two integers a and b, where you can consider b to be positive and a is any integer. Then what you do, you first calculate the bth root of a, x. We know how to do this, okay, and we have already proved that for every positive real number, such a bth root exists for any positive integer b. And then what you do, because alpha a is any integer, you raise that thing to the eighth power. So by that old definition, this is x to the power alpha. By the new definition, this is x to the power alpha. If we just look at these two definitions, there is no immediate reason to believe that they are going to give us the same thing. But if that we don't get the same thing, then there is a problem. The two definitions are not consistent. So now we are going to see that we do get the same thing. But how? Since we have the sequence Q of rational numbers that converges to Q, definition 672 gives us x to the power alpha equal to limit of x to the power q, that is equal to x to the power q. Do you see what we have done here? I mean, one can of course find any sequence, whatever sequence one can find, that converges to the rational number q, some sequence of rational numbers. But among those sequences, there is a particularly easy sequence that converges to q, which is the constant sequence, all of whose terms are equal to q. Because q is rational, so this constant sequence is a sequence of rational numbers and it converges to q. So using our new definition, x to the power alpha will be the limit of this sequence x to the power q. Because of the constant nature of this sequence is also going to be having only one term. Okay, I should not say one term, a sequence has infinitely many terms, but only one distinct term, x to the power q. So what limit here we see, that is the limit of a constant sequence of real numbers, which of course converges to that single value, and that single value is this power x to the power q. So our x to the power alpha calculated using the new definition equals the ordinary x to the power q calculated using the old definition. So these two definitions actually give us the same value and there is no problem. And this shows that our new definition is indeed an extension of the old definition, not something totally different. It includes the old definition in itself. Now, fine, we know now what the meaning of x to the power alpha is. But now the question is, can we extend the rules of exponents also to this new general setup? And we can. For that we have this next proposition 673. All the results all the results of lemma 5, 6, 9 which held for rational numbers q and r. Q and r are exponents. You go to the statement of this lemma, you will understand. Continue to hold for real numbers q and r. And the proof is very easy actually. Only a part of the proof is available here. The rest we will do in the exercise, the sole exercise of this section. We demonstrate this for the identity x to the power q plus r equal to x to the power q times x to the power r. That is the first part of lemma 569b. That part b itself has another part, x to the power q whole to the power r is x to the power qr. The other parts are similar. And are left to exercise 1. The idea is to start with lemma 569 for rationals and then take limits. To obtain the corresponding results for reals. Okay, no need to write that much. Okay, so let q and r be real numbers. Then there exists, I need ink again, just a little bit. then there exist sequences Qn and Rn of rational numbers converging to Q and R respectively. That means Qn converges to Q, Rn converges to R. Then by the limit laws, the sequence Qn plus Rn of rational numbers converges to Q plus R. Okay. Now by part B of lemma 569, x to the power qn plus rn is equal to x to the power qn times x to the power rn for all positive integers n. Note that we are able to apply this lemma in this case because those qn are in, they are rational numbers. Q and R are general real numbers, they may not be rational, but these are rational, so for them, for rational exponents, we already have the law. Hence, by definition 672, x to the power q plus r. Okay, what is x to the power q plus r? We need a sequence of rational numbers converging to q plus r. Such a sequence is this. So by our definition of real exponentiation, this is equal to limit of x to the power qn plus rn, which is equal to limit of, use this one, times x to the power rn. Now use the limit laws. This limit will be equal to the product of these two limits. Times and this converges to q, so that means this limit is x to the power q. By the definition again, by definition 672, and this limit is x to the power r. So that is just the law. Just like that, we can prove the other laws. And one more thing we have to remember when we start the exercises in the next video, that actually the proof of lemma 671 is not over. We still have to prove it in this case. So we will handle that case first, complete the proof in its entirety, and then we prove the remaining parts of lemma 569 for real exponents. So here the section ends. Now let me say some general things about sequences before we end the video. Why are sequences important? Sequences are important because a sequence is an infinite process. A sequence is a list like this, where there are infinitely many terms, but there is a first term, a second term, and so on. So using the idea of sequences, by now you have seen we have defined many things. We have in fact defined such a complicated thing as x to the power alpha. If we look at such an expression, alpha is say 2.316. Of course, this does not mean multiplying 2.316 number of x's. That does not make sense, but we now know what that thing means. Now, we will later see that just like we are on the real line, there are objects called metric spaces, where just like the real line, there is a notion of distance between two elements or 2 points. In such spaces, sequences are important because sequences can lead you from one point of the space to another using, of course, infinitely many steps, getting ever closer and closer to your objective. And that's how we have defined convergence now. So this getting closer and closer, this thing we will make sense in terms of distance, just like what we are doing here. Now, you are using infinitely many steps to get to this from somewhere, which in another interpretation can be looked at like this. You want to say something about a quantity, you cannot say that at once. You are approximating the quantity using things that you already know, but using an infinite process. So that is the jump from algebra or arithmetic to analysis. Algebra has finitary operations or processes which do not involve infinity, but analysis or calculus captures that infinity. So the notion of a sequence and particularly its convergence can be looked at like this. A sequence, or rather the limit of a sequence, is something to which the terms of the sequence are approximations. The fact that the sequence converges to the limit, it translates into this fact that this approximation can be made with as much accuracy as you want. That is, the error can be made as small as possible. Now, in this whole scheme of things, these places that you see around your objective, they may not behave like what we see in our ordinary geometric Euclidean space. They may behave in some strange manners. In metric spaces, things are okay, because a metric space is a first countable. These things will come, okay, when we study topology, first countable topological space. But there are some spaces where these areas or these regions around a point are so numerous that any sequence falls short. It never reaches the your objective. No matter how infinitely many steps you take, the kind of infinity that you see in a sequence is the smallest possible infinity, countable infinity. In some spaces, that is not enough. So in such spaces, sequences become useless. You have to use other things, nets, filters. Okay, so since in analysis we mainly deal with metric spaces, sequences are important, and we already see how important they are. They have already been used to define real numbers. We used sequences of rational numbers. They have here again been used to define exponentiation, and again we will continue to use sequences. But I will give one example of a space when we study topology. Here itself in Terence Tau's analysis, where this peculiarity will occur, where sequences fall short of they cannot reach the desired location in some sense. So we will see these things. So because of metric spaces, sequences are important. In general topological spaces, they are not that important. So with this, this video is over. Today is Sunday, no? So next Tuesday, what are we going to do? We have already seen vector spaces, groups, fields, vector spaces. So the next one, let us do calculus. Next Tuesday, let's do calculus, and then we will go to number theory and then graph theory. So that will be all. If you want to say something about these things, you can write in the comment section below, or you can send me a mail at my usual address. So see you on Tuesday. Until then, have fun with mathematics. This is me, Lucifer, from a mathematical room. Have a nice night.